Hey guys, how you doing? I think we're ready to get started. Tonight we have a really great speaker, Ralph, from Argonne Lab and a teacher at IIT. I'll do a lot of introduction because he has a lot of acronyms that he's going to have to account for on his own. But it's a great talk. We've had a lot of conversations lately. He's been part of the kind of regular meetings with the computation group here in Chicago, and I think that it's great that you had an idea to have a talk, and I'm sure it'll be a great one tonight. Two things. One is if you haven't had a chance to check out the website, because we've been posting videos of the events, and this event will also be posted. So if you get a chance, or if you miss an event you want to pick up, you can watch it. And it also has announcements for the next events, and the next one in June, towards the end of June, will be hopefully a group from Gensler Design Research Group. So, thanks.
Thank you, Anthony. So, as Anthony said, I'm Ralph Muehlisen from Argonne. We can dispense with most of these in case you're curious, fellow. ASA is the Acoustical Society of America, and INS is Institute of Noise Control Engineering. So before I started doing building energy stuff, I spent 20-some years doing mostly acoustics. It's been the last 10 years or so that I've been doing building energy stuff. I am a principal building scientist and the lead of BETTER, which we will explain in a second, at Argonne National Lab, which is, at least at this point in time, in Decision and Information Sciences Division at Argonne. I know that many of you actually worked at Argonne on different projects or are thinking, are proposing. So I'm actually a researcher. I'm not in facilities. I do research for the Department of Energy related to building energy efficiency. So you guys don't interact with me because Decision and Information Sciences doesn't get new sexy buildings. It doesn't necessarily. About the closest thing is they came by. I say they. It was who was it from? It was people from Grumman Buckus were coming by. They had got a contract to they were looking at energy efficiency of the existing buildings, and they were doing thermal imaging of lots of offices. So they came by our building and said, "Oh my God, this is an awful leaky building." Yeah, so when you're a researcher and you don't have a sexy thing like huge energy, a huge supercomputer, or something with the term bio inside the name, you get stuck in a dismal old building. And that's where I work. But the buildings program, as part of a division reorg, is moving to energy systems. And so I get to go to another dismal old building when we physically move and enter the new division. So at least for now, I'm in Decision Information Sciences, but soon to be over in energy systems. Some of you know me as I still am a professor at IIT. I used to be full-time faculty. I'm now just an adjunct. I started at Argonne in about 2011, but before that I was at IIT, director of the architectural engineering program. Before that, just a regular faculty. Before that, I was at the University of Colorado, and you don't have to keep going back further than that. So, as a quick overview here, you saw the acronym BETTER. I'll explain what BETTER is just a little bit so that you have an idea of where we're coming from. I'll talk about the big problem of why I'm even worried here about energy modeling, and the small problem, but explains this particular talk. And we can talk about probabilistic energy modeling, Bayesian calibration, and we can finalize a little summary here. But BETTER is the Building Energy Decision and Technology Research Program at Argonne. We've got a main focus here of trying to develop decision support tools and technologies for energy efficiency in buildings, or at least increasing energy efficiency in buildings. We will hope that we can teach you to apply these tools to make better decisions within your buildings. And then we transfer this over to engineers, designers like yourself. The idea here of decision support tools. This could be something like building energy modeling, making building energy modeling better. It could be something like innovative control systems for HVAC. That is a decision process. Now, it's a decision process within the building that the building's doing by itself, but it's a matter of something sitting here looking at a temperature, looking at humidity, and deciding to turn on a piece of equipment or turn off. It's a decision process. So the idea here is we want to go and, instead of doing technology development, we're looking at decision science. And part of the reason for that is there are other labs that the Department of Energy supports and companies out in industry who are doing good technology research. Oak Ridge National Lab, National Renewable Energy Lab, Pacific Northwest National Lab, and Lawrence Berkeley National Lab all have big buildings programs. They get $50 million of research each. We get 2. So jumping in, and they've got laboratories that have facilities that we don't have, and they've got 100 people who are working entirely, exclusively devoted to buildings type of stuff. We've got only a few people exclusively devoted to buildings. So it's we're looking at things a little differently, but we think we've got a niche because we specifically want to talk about decision support. And the idea is trying to find ways to help you who are out doing design work, design better buildings with better tools, to help the people who are making decisions, the owners, the financiers, find ways to overcome the barriers that they're seeing. Why is it that they don't choose the energy efficient alternative when it looks economically feasible? Sometimes it's a matter of capital things, that money's in different pots. Other times they're sitting here saying, I don't trust that you tell me you're going to make this back in 5 years or 2 years or 1 year. So this is actually a large group. There's a lot of people who are involved. There's Leah Gazowski, some of you know Leah, and myself are the overall leads of the program right now. We've got people working in a number of different areas. The hardcore group right now is Leah, myself, Todd Levin. We just recently hired on Brendan, who's here, as an STA. Almost everybody else here who's on the list is working on projects in other than buildings at the same time. And so everybody on this list either work on a project that they've actually been able to charge time or help develop proposals that have been funded or not funded. So it's a large group, but the core is still really rather small. So the reason why I'm coming here to talk, and I want to try to tell you why you need to worry about uncertainty and calibration, comes with a big problem. We got the world is melting. It is melting. It is melting. There is no question. If you talk to any owner, any decision maker who questions that, I don't know how you get past it, but just realize that you're talking to an idiot. I hope you all realize it. There is no question about climate change. I don't even think that there's a debate as to whether it's man-made, but there is no question about climate change. We have the polar ice cap is melting, Antarctica is melting, and we are past the point of stopping the melting. We are now into a point of trying to mitigate the problem so that it doesn't get any worse than it could be. Where it's really coming from is CO2 emissions. And we have a situation of, if we do projections and look at where we're sitting, this graph showing you the CO2, the billions of tons of CO2 going into the atmosphere per year. We have the situation from 1990 to 2000 was going, we had a drop as people started taking a look and doing some mitigation. We have a big problem in terms of the building stock growth going back up. Part of this drop in 2008 to 2010 was a nasty economy. It's recovering. You guys have jobs. At least most of you do. How many of you didn't have jobs after 2008? Oh, good. That is good. Because there's an awful lot of architects and engineers who just graduated and only been working for a year, who had no jobs for a while. So we had a downturn, but things, if we don't change the way we're designing buildings, and you all know about AIA 2030, you all know about Department of Energy stuff, but if things don't change the way that we hope to, this is business as usual. In order to mitigate the situation, this is what we have to get to. We have to have levels coming down not by a factor of 30%, not by a factor of 50%, not by a factor of 75. We got to drop the CO2 levels by a factor of 80 to 90%. The mitigate is just trying to avoid the catastrophe that people are really looking at in terms of uncontrolled meltdown. So, we need to stop this. It's like, okay, what do buildings got to do with it? If you don't already know, this is a reason. Take a look at the energy use in the U.S. This is a breakdown of the energy use in the U.S. And if you talk to most people, what's the biggest energy user in the U.S.? People often think, oh, it's got to be cars, transportation. Nope. It's got to be our manufacturing industry. No, it's buildings. It's buildings. Buildings use 40% of all the energy use in the United States. If you actually break down heating and cooling of buildings, is
over 20% of all the energy used in the United States. If we just were able to stop all infiltration and all the energy associated with infiltration, it would be 4%. 4% of all the energy used in the United States. Buildings are the biggest contributor to that and to that. It's buildings. All the stuff that you're designing. All the stuff that I'm trying to help you design better. So, if we reduce the energy use of buildings, we're going to reduce the CO2 and we can save the planet. You can do it, I can do it. We've got to work together, but we can do it. Just looking at retrofits, not even looking at new designs that most of you work in. If we can go ahead and do retrofits where they're available, we can cut that. Looking back out here to our numbers in our other graph, we can take a big hunk of this right in here can be made just from retrofitting existing buildings. So that the question that comes up when you start talking is, we can't afford it. We can't afford it. Maybe this is a bad problem, but we can't afford to do it. There's nothing we can do to really solve this. It's a matter of, if you go take a look at studies, there's a lot of good studies out. One of the most important one, the McKinsey report that was done here in 2008, and then this other one that was done by Deutsche Bank in 2012, looking here at the economics of energy efficiency. And specifically, unlocking the efficiency in the U.S. economy isn't exclusive to buildings. It's also including manufacturing and transportation. But if we look here at retrofits of the buildings, harkening back, you really got to look at this as an investment. If we look at it as an investment, it's almost $300 billion that's available. And energy savings over 10 years of doing the retrofits that are available that we could do today, that we can do on buildings like this one, it's $1 trillion that we can pump into the economy and save. The other thing, at least any time you work with the Department of Energy, energy savings is the #1 goal. The #2 goal is job creation, because everybody in government cares about job creation. Retrofits are job creators. So in addition to $300 billion investment opportunity and $1 trillion that's going to be energy savings that gets pumped back into the economy or into some rich person's pocket, there is several million jobs that are sitting here waiting to be created. And most of these jobs are not necessarily one-off little jobs. These are, when we start creating an economy, we start creating a market, you have jobs that are blue-collar or white-collar. And if there's any other collars, they're probably involved too. If we're talking new buildings, it doesn't cost too much. You all can go out. You can, if you really try hard, you can do a net zero building with no extra cost. But if you go and say, all right, we're not going to really compromise some of the things that I like to do, my standard design, there's no reason why you shouldn't be able to do a net zero building for anything that's small. I mean, we're not going to do a net zero skyscraper, but net zero 5-story or below. There's no reason you can't do it with no more than a 15% increase. And now I say, so with a 15% increase in the energy savings, it's got a few-year payback. You're saying, well, few-year payback doesn't really come in. I've got capital cost up front. 15% is not that big a deal. That's saying I got a $10 million building is becoming 11.5. That's inside what you put in for your contingency. You can do this. So that's our motivation. How do we go ahead and get people to either look here and say, I can convince my owner to spend that 15%, or convince my owner to do a retrofit? What we have are barriers to this, and a lot of the barriers are economic. So as we get going here, one of the things here, I want to get some terms out. I'm going to use the term EUI, energy use intensity, which is an energy use per unit area. So I like to work in units of kilowatt hours per meter squared. Anybody who practices outside of the United States likes useful units, not stupid ones like BTUs. So sometimes I work in kilobtu per meter squared. The Department of Energy tends to like kilobtu per foot squared. I know that's what most of America likes. Maybe we can convince them at the same time to make changes to change our units. If they can't, just live with me. Kilowatt per meter squared and kilobtu per foot squared is different by a factor of 3. So when you see me talking, if I say 100 kilowatts per meter squared is an energy efficient building, realize that if you convert it to kilobtu per foot squared, it's like 30 something. So EEM and ECM, energy efficiency measure and energy conservation measure. The idea here is this would be something you do either an energy efficiency measure, is if I'm doing a new building design, we usually use this term, that I'm going to make a change in design to reduce energy use. When we're talking about a retrofit, almost everybody uses conservation measure because we're trying to reduce what's already used. Two other terms that I will use toward the end. PDF, it's not a portable document format, it's a probability distribution function. And a CDF is a cumulative distribution function. We use these to describe probabilities. All right. So, as we get started here, one of the things to think about is where energy modeling fits into your new construction. And whether we're doing a traditional design, bid, build, or design, build, we're sitting here, we got our stages of conceptual design, schematic, design, development, construction, and we got design, build, there's overlap. Maybe you even kind of just mush these together into schematic, design, development, one big mushy thing. But the idea is, where does energy modeling fit in? And it basically, right now, most people do the bulk of the modeling here at the edge of schematic, beginning design. Forward-thinking designers want to move it forward, but the idea here is we're not doing it at construction, and we're rarely doing it, at least much, in conceptual design. So if we look at a curve of project progress, this one actually is coming from one of the BIM manufacturers. But this is an interesting plot that many of you have probably seen before. It's a plot here that we talk about. This purple line is the ability to impact cost and functionality in terms of change. We're talking about when changes occur. They occur in conceptual design. It's easy to affect cost and functionality. I go ahead and it's easy enough to do this. And the cost of design changes is small, but I often have no idea about the impacts of these things. As I go farther into progress, it is much harder to actually affect impact and cost and functionality, or the cost of design changes go up. When we get out to DD, there is no chance anymore for me to rotate the building and change the window-to-wall ratio. At this point in time, everything else has been fixed. I change the window-to-wall ratio. I got to change my lighting. I got to change my HVAC. I can't. I can do that early on. And if we look here at curves of when we're doing design build, this one's called designing with BIM because it was a BIM manufacturer. Basically, this is design build versus traditional design. Design build, I have more ability to do changes early on because I'm working schematic design in with design development. Where do we want to work, though? When we're doing energy modeling, we want to sit up here right at the beginning. We want to see as close to conceptual design as possible. And that's where many of you are hoping to go. You're waiting for the tools to come to go there. But even with this in mind, doing the modeling up front, there's a problem. And this is, let's start out. We got a building, don't have to name it. You sit down, you do your napkin, and then as you're working and you come back in, you get your Rhino up and you start drawing a picture, or in this case it was SketchUp. Doesn't really matter which we go ahead and we take our drawing, we turn it into a BIM model, and now at this page we've got some massing, we got an orientation, we know where it sits. I want to start doing an energy model. And your energy model looks like this. No, this is fuzzy. I really don't know what's going on here. I don't have a good idea of dimensions. I don't have a good idea of the materials. I don't have a good idea of window-to-wall ratio. You drew this up. But I know you're going to change it 25 times before the next time you come back and ask me for a model. And you would have asked me for a model every single time if you could send me that many emails. You're going to change the interior. You're going to change the exterior. You're going to go ahead and change the systems. And so I've got a fuzzy mess that you're asking me to model. And you're asking me to give you a number. You're asking me to tell you that when I move this column up and down, how much energy is going to change. And I don't even have a freaking idea what you want to put in for an HVAC system. And you're asking me to give you numbers. So this is a hard question. I don't have hard numbers. I've just got fuzziness that I'm thinking about. If instead of new buildings, we're doing retrofits, who here works on retrofits? Okay, we have a retrofitter. Thank you. We need to have some architects working on retrofits. Existing buildings is a different beast. Here we go ahead, we know what a building looks like. I can take a picture. There is no question. I not only know what the building looks like, I know how much energy it uses. Kind of. So we take this and we'll go ahead and I can take pictures, and actually now with a pretty cool programs, I can take pictures all over, and a little bit of Google Maps. I can go ahead and have an automated CAD drawing, but I can't model with this. This has got way too much detail. Even though I know all the stuff, this is way too much detail for anybody to try to model. So we end up with a box that looks like this. I got the windows in the right space, I got the right height, but I cut off all the details. So again, I'm taking something that is existing and has got lots of detail and turning it into something else. Whether we're sitting here that I've got an energy model that doesn't or can't reflect all of reality, or I've got fuzziness because I really don't have a clue as to how the building's going to come out. Even if you as a designer don't change your design, I don't know the details of all the components that are going in. Nobody does at the conceptual design phase. We're sitting here in a situation of not knowing. Not knowing is uncertainty. And uncertainty leads to problems with prediction. So we now get to a point, everybody, we go here, we got a model that we think we want to do, this fuzzy model that comes from an architect and now through the designers. We now have our building model, and we got to throw in all the software. We also have lots of modelers, lots of different software, and each one of these software packages has different ways of trying to implement the model. And for us to go ahead and as modelers say, I'm going to give you a number and tell you how much energy it's going to use, is something that's fraught with error. So our big problem is what the heck are we going to do about the meltdown? And I think we need to make buildings better. We got a small problem, though, in terms of energy modeling helping out. And this is it. Energy modelers are liars. We're all liars. Who here is an energy modeler? Okay. You're liars. We're all liars. We are. We're absolutely liars. Because when we get done, we go ahead, we take what the designer asks us. We put it into a box and we give you a number. And we give you a number we know is not going to be the end result when the building's built. And I know when I predict an existing building, I know it won't match up. And actually, I'm going to say that the people who model retrofit buildings are even bigger liars. Because when we're done, we tweak our model and it matches, but we just tweaked our model and it matches. We don't even know if we got the inputs right. When we're doing conceptual design, what we know about our inputs is right because that's what we were told. We just don't know how it's going to match reality. Now we've matched reality by changing inputs in a way that we can't be sure is right. So this is how things really work. This is what we usually do to predict. We're done. Somebody told me how much energy, how much it will cost. I give them a number. 80 kilobtu per foot square, $140. This is my preliminary design. This isn't what we should do, though, because I know that number's wrong. If I'm good, what we should be doing, at least giving you ranges. Here's my range of energy use. Here's my range of cost. And actually what you can do today, actually when you're done, you can't just do it from my talk, but you'll know that it's capable, there's an ability. It's something like this. This, if I knock down this wall anymore, this is what you ought to be doing. You ought to be going out and telling me what's the range, what's the confidence levels. I'm most likely here $140 and about 670 kilobtu per foot square. But this is really my range of uncertainty, my range of possibility. And this helps me start doing a lot more detailed analysis. I can go ahead and say, oh, what's the chance that it's going to cost $145 a square foot? What's the range of energy I can expect if I spend that much money? This is the same data. If we start now looking at this as a big data problem, instead of just this contour plot, I can start looking at probability distributions and slicing and dicing, and got lots of different ways to present the material. But basically, it's the same idea. What you really want to do is get an idea of the probability of the energy use. When you're starting at a beginning building phase and conceptual phase and I don't know the details, let me take that as an uncertainty. When I'm done, I get a probable energy use out based upon probabilities of what the inputs are going to be. When I'm trying to match up an existing building, I actually have probabilities that the inputs to my model are right. And when I adjust them, I will get a probability distribution that matches the output. And then I have probability and uncertainty in all the inputs, which is important when I'm trying to do a retrofit analysis and predict how much energy I'm going to save. Here's an example of a retrofit of why this is a problem. Here we got a situation where a typical energy person said, here's a base case, here's the energy savings we expect with an HVAC retrofit, and the energy savings we expect with an envelope retrofit. Suppose they cost the same. We're not going to go with the fact, well, usually HVACs, suppose it costs the same. And if you naively look at this, you'll say, I should choose the envelope. Envelope is going to save me a little more energy. And then when you sit down and you talk with the owner, and the owner says, well, which one is more likely to possibly either cost more or cost less, or which one has more uncertainty in the energy savings? You go, oh, well, I think the envelope has more uncertainty in energy savings. But without quantitative numbers, it's a difficult thing for you to go to the owner and argue envelope versus HVAC. And I will argue in a case like this, envelopes, doing a change in the envelope is always going to have a lot more uncertainty. Because as soon as you start plain changing one envelope, you've got so much more construction and possibilities that things that can go wrong. And uncertainties that creep in as we start changing windows and the seals and possible infiltration compared to HVAC equipment. A typical situation might be something like this. These are the probability distributions. So here's my baseline, and the reason why there's uncertainty, you might say, I have a base building. I measured it. I know what the energy use is. It's a single number, but it's not. Because my energy use for this year is not going to be the energy use for next year. The energy use for January of one year is never the energy use of January the next year. There's a variation. Variation from weather, variation from occupancy, variation from the equipment degrading. So even when I think I know what the energy use is from a measurement, I don't know what it's going to be next year or the year after that. And I have to take that into account in my prediction of the base building. So my prediction of how much energy I use this year is, or what I'm going to use next year, how much I'm going to save, can't be a single number. There has to be uncertainty with it. So the idea is here, I should be able to predict the uncertainty in the energy use next year. I predict the energy, the uncertainty in the energy use of the HVAC equipment in the envelope. And if I look at these curves, the peak of the probability for the envelope is to the left of the HVAC equipment, which is where these numbers might be coming from. However, if we also take a look, there's a good chance when I do this envelope change, I can have really reduce the energy use. But there's also a pretty good chance that it's actually going to be much higher, or at least higher than the HVAC. So this plot by itself doesn't convince an owner. But when you look at this and say, oh, what's the 95% chance that the EUI is less than some number? You look at the red curve of the envelope, and you look down here, and it's probably going to be, I can say with 95% certainty, it's about 240 kilowatts per meter squared or less. Whereas with the HVAC, that probability is 218. And if the cost is the same, even though the peak was higher, I got a 95% certainty I'm going to be less with the HVAC than I am with the envelope. So you go and do a risk analysis. Where is it you want to put your money? If you're a betting person, say, which one is going to be the highest chance of having a low EUI? You choose the envelope. If you're risk averse and say, which one has the highest chance of not failing? You choose the HVAC. And I can't give you, I'm not going to tell you what is the right way to decipher this. But the point being, just this curve on the left doesn't give you enough information.
Ralph, can you clarify what the base is?
The base, this would be the building as it exists now before I do a retrofit.
Okay, great.
All right. So one of the things I know a lot of people like to do, especially when you're doing conceptual work, I will go ahead and do parametric variation. Now there's reason to do parametric variation. I want to look at, as I change my window-to-wall ratio, how's the energy change? That's something that makes sense and you do it. But then they come back and say, I'm going to do a parametric variation to see the uncertainty. Uncertainty and parametric variation aren't the same. Uncertainty says I'm going to characterize what I don't know about the inputs. We can do the Donald Rumsfeld. There's things that we know. There's the things that we know that we don't know. And as modelers, we really avoid the things that we don't know that we don't know. However, the idea of doing uncertainty is quantifying what we don't know. We don't know the numbers, but we can put limits on it. But some people say, all right, I don't know the COP of my big HVAC chiller. Let me just wiggle it a little bit, and I'll tell you that's my uncertainty. Uncertainty estimation means quantifying bounds and properly using that in cooperation, or at least in conjunction, with the uncertainty of other elements. You can't just do a sweep of one and a sweep of another and hope that it all works together. The reason being buildings are very nonlinear. if I increase the COP of one piece of equipment, and I change the SHGC of another piece of equipment, and I change the lighting intensity, those things interact. And I can't say that just by changing one it's independent of the other, which means you really have to work at them all together. You can't just do parametric sweeps and hope that you're going to get the right numbers out. So, don't do it. Parametric sweeps are useful when you want to see variation in parameter, not when you want to do uncertainty. And the reason I'm putting this out is because a lot of people will confuse the two. What you really ought to be doing, if you ask me, is putting together uncertainties of distributions for things that you know are uncertain, things that you're pretty certain about, and when you're doing a beginning building and conceptual design, these may be hard numbers. If you're actually doing an existing building, it's not uncommon to have 3 people go through and have a 10% variation in what you measure the area of the building. So that's something that's actually uncertain. Height of the building is pretty well known. When we're done, we put these uncertainties, these distributions that tell me the probability for any of the inputs into an engine, and I get out one of these probability distributions. So what I want to talk about, the bulk of this talk, I guess the rest of it here, is how do you start and approach this? I'm not going to be going into details because I don't have the tools available completely for you. People are doing this today with existing tools. It's going to get easier as things like the Open Studio Software Development Kit really put wrappers around to make this easier to go. But the basic idea is here is you're going to choose the inputs that you think are uncertain in your model. This is something that requires expert knowledge. We're then going to put this in a Monte Carlo that we're going to sample from the PDFs that describe the inputs. I'll describe this in more detail. Run the model, save it, and check and see have we done enough times. Have we picked enough points? Is our output getting stable? And then we analyze the output. So let's kind of go through these steps. The key first step is sitting here and thinking about what inputs you're going to work with. So let's look at our input selection. The basic thing is we're going to look at our model and figure out which inputs are uncertain, which ones aren't. Which ones do we have good amounts of certainty and which ones do we not? So as we go into a building, I will always tell you, if anybody asks, you always assume infiltration is uncertain. I don't care if you've got the best curtain wall and we got nothing but glass and I've gone, it's a high rise, so it's been pressure tested and it doesn't leak. You still got people coming and going by those doors at the base. And unless you have a super, super high rise, I know some of you work on those, there's enough people coming and going, and infiltration is an uncertainty. Anything less than a high-rise curtain wall that is really pressure tested, uncertainty is a biggie. Anything that's got openable windows, infiltration is a big uncertainty. Occupancy has to be uncertain. We never have this. In fact, going to stochastic models that try to do probability predictions of occupancy and where people move in buildings is kind of the next step where I think modeling is going to go. But right now, we just have to say we don't know. Maybe we can characterize a variation. Area, probably not. Height, probably not. The COP of our cooling equipment, if we're in beginning design phase, that's certainly an unknown. If I'm doing conceptual design, heck, I might not even know if I got a chiller. Maybe I've got 4 or 5 different technologies, and the effective cooling COP will change by a factor of 2, 3, 4, depending on what I choose. The U value of the walls and the windows. Unless if I'm in conceptual design phase, that's an unknown. If I'm looking at an existing building, it's certainly an unknown. So, well, I know those windows. You tell me. You go to any window manufacturer and tell me what the U value is. If you look up the U value from 25 years ago, because it's an old building, it's not going to be what it is now. When we include all the thermal losses in the frame and the infiltration that kind of comes along with it, and if you can even find good measured data for that old window. And we look at walls. Walls are, forget about trying to guess the U value of walls. It's really a hard thing to do. All you can do is put uncertainty bounds on it. So once we've figured out which ones are uncertain, then we have to assign distributions. And I'm not going to suggest that this is easy. This is hard. This is an area of ongoing research. One of the things we're doing at Argonne, and we've got colleagues out at Georgia Tech, and there's colleagues out at, I think there's people out at Berkeley, and there's people out at Penn State. We're all working here trying to figure out what are the uncertainty in these inputs. Most of our focus has been on retrofits, but the same information can be used for conceptual building design. In that case, it's often not a matter of, I think there's actually some unique research that has to go in. What is the possible range that I have? Given even if I know that I want to use a certain type of glass, what are the variations that from the pool that I might get of manufacturers that get chosen as part of the design process, the construction process. All right, so once you've got the inputs, one of the things I left out, actually, is you don't have to put uncertainty in all the building inputs. An energy plus model quite literally has thousands of inputs, thousands of parameters that you vary. What you often need to do is figure out the most important and influential ones. Maybe there's 5, maybe there's 10. If you're doing conceptual building design, you might say that there's 20 because you really don't know the interaction. But you limit yourself as to what you think are the most important. And you can actually do sensitivity analysis of the model once you have a base model to see, oh, are some more important than others? If one ends up being more important, we'll put this on the list and we'll make it uncertain when we do our more final runs. I didn't have time to really get into that. So the next thing is this Monte Carlo loop. I figured out what inputs are uncertain, and I have to do the sample, run, save, and check. So the big thing here is sampling. And I want, for those of you who are following along and say, yeah, this all makes sense, and I think I can go up to this point, I want to emphasize the importance of how you sample that PDF. Sampling the PDF, if we go back here, means picking a random number according to its distribution. And the idea here is where there's a peak number, it's more likely to happen. So I pick a random number, and I kind of check here. And occupancy said it should be wherever that peak is, be the most likely number. So I pick 100 numbers, I will get out a curve that looks like this in terms of the number. And there's going to be a few that are up here, a few that are down here. Most of them are going to be in the middle. And so sampling is picking a random number that's defined by this distribution. But you can't just kind of pick random numbers randomly. Monte Carlo methods, what most people do is they'll pick, I know the distribution, I pick random numbers. And that works if I have enough numbers to do. And when I've got 20, even if I'm only doing 10 inputs that I want to vary, I may be going and drawing hundreds of thousands to millions of numbers. That means hundreds of thousands to millions of energy model runs. And when you think here that it takes 5 minutes to do an energy plus run, that's a little bit time consuming to do 5 million of them. So we need to find a better way. There is another way, it's called latent hypercube sampling, that samples the distributions more evenly. I'm putting this out here so if you start looking into this and say, I can start doing this now, don't just use random sampling. Go look up latent hypercube sampling to understand the difference. Here's an example of drawing from a triangle distribution where we did 300 times. And we use latent hypercube sampling. The distribution comes out, looks like a triangle. And this is what comes out of random Monte Carlo. There's so many gaps here. That means, what this means when we do my prediction at the end, I don't have enough data to have reliable statistics. So using latent hypercube sampling helps you to choose numbers so that they sample the distribution more evenly. And when I've got 5, 10, 15 inputs, the more I can use things like latent hypercube sampling. I can go ahead with 8 or 10 inputs and only have to do 600 or 1,000 runs instead of 60,000 or 100,000 runs. That means it's actually practical to do when I throw it up on the cloud in a few minutes. So here's a couple of curves to help convince you that I can converge to numbers a lot quicker with latent hypercube sampling. Basically, these curves down here showing you how quick we get to reducing our error. Another problem that I don't have an easy solution to, although conceptually we have, is correlated inputs. Some inputs are very correlated. The occupancy of a building, the lighting power load, and the electric load are very correlated. Lights go on when people come into a building. Power goes on when people come into the building. And when my schedule says people are going to be in the building, I have a higher lighting load usually. I got a higher plug load. And the two things are not independent of each other. So if I choose them as random numbers, it doesn't make sense for me to choose a plug load that's on the high end and an occupancy on the low end. That would never happen. So what we have to do here is, here's an example of things that have no correlation. If I choose one random number and another, and I start plotting, actually looking at occupancy versus plot of occupancy here versus plug load here, I get a scatter diagram that looks like a nice circle. If there's correlation, I get things that are more straight line. It means when occupancy goes up, plug load goes up. And that's a typical thing in a building. So identifying those things that have correlation is important, because if you don't do that, what you end up is you overemphasize the uncertainty in the energy model. So one of the solutions of this is joint distributions. I don't know of any people doing research or in any of the packages that actually have joint distributions set up for this, but this is one of the things I definitely want to investigate over the next year as far as research goes. I'm going to be asking for money from DOE next year as to how we can, setting up the workflow so that we can identify, or if we know, do this joint distribution system for uncertainty modeling. Okay, let's go ahead here. So we sample from the PDFs, we run the model, we go around and do this tens of times, hundreds of times, maybe thousands of times. Maybe we want to check and look for the distribution to get stabilized. When we're done, we got a bunch of numbers. I got 600 runs, I got 800 runs, I got 10,000 runs. I got a lot of data. And I'm going to look at the output. So one of the things that we want to do is, I would argue, you want to look at probability distribution functions. This is a histogram. I look and see how many times I got the 150, how many times I got 154 within bins. And then I divide by the total number of runs that I did as well as the bin width of the EUI, and I get a probability distribution. Now this is one where I didn't use Hypercube sampling. We can see how even with 1,000 runs, this is pretty choppy. If I now go ahead and actually add up this curve, I integrate this curve, or I add up to a certain number of the PDF, that tells me what's the probability that the energy that my building will have is less than or equal to this number. So if I say, what is the probability that it's less than 150? I can basically do that. I add this up as I go along, and I get what's called a cumulative distribution function. And this is actually the curve. As much as people like to look at it, this is a more useful curve. This U-curve is great because the CDF of 50 is my median. That tells me I've got a 50% chance of my energy being above it or below it. I can look here and see where the CDF is 0.5 and 95%, and those are my 5%, 95% bounds. My standard deviation actually is between 33 and 67. I could get my standard deviation out. This curve gives me those statistics that I want for doing risk analysis. This is the curve that anybody who's a banker looking at investment wants to see in my investment. So they can say, what's my chance of not getting my rate of return? And if my EUI, I tie that to an energy cost over a certain number of years, I can do a rate of return right off this curve. If I'm sitting here and trying to do an early design, and I want to know, am I going to meet my EUI requirements for my lead points? Am I going to be lead silver, lead gold, lead platinum? This curve again tells me the probability I'm actually going to make it. Now, given that lead at this point in time doesn't have you come back and double check when you go ahead and do your design, you don't need this curve. But when lead catches up to reality and they realize, well, they already realize now, but things are able to change, it's like, oh no, you have to do a follow-up. People are going to be a lot more likely to want to know the risk of failure. So there are a lot of smoothing things we can do. So one of these things is called kernel density estimation. I actually tend to like this. And this is actually looking at the statistics. And given the statistics, you try to extrapolate, what if I had done this 1,000,000 times, and you get out a smooth curve. All right. So what good is all this? Here's what I'm getting to get. If we are talking new construction, we have a possible range of the EUI. You have an idea when I'm done, given this fuzziness at the beginning, what can I really expect out? So that I'm not telling the owner, I'm going to get 150 kilowatts per meter squared. You're really saying, no, it's going to be between 120 and 170, most likely 150. But you can be honest, and you can, within the design community, decide how important is it that I narrow that down. That's going to be a restriction on your design. If you have a target, this is one of those things that helps you constrain your design space. What I also think here, as time goes on, we're going to have changes in performance metrics. Lead is not going to have a single number. Lead's going to be saying, you have to give me a 95% confidence interval. I see building energy code doing the same way. When this becomes a commonplace situation, that's how things are going to go. They're going to be asking to give an uncertainty along with the number you predict. And whether you do a confidence interval or you say, you need to have within 10% accuracy, within 20% accurate, an uncertainty. I shouldn't say accuracy, uncertainty. With a methodology of what the inputs are. There'll be standardized tables. We also get the idea of the risk of the design options. You will see as you look here, if I go to this new system that has a lot of unknowns or there's a lot of possibility, one of the things you can put on the uncertainty is how it will actually be installed and how it will actually perform as installed. Things that are risky, that are a lot less likely to give you the single number out that the manufacturer has, you can take that into account. And if it's an important parameter, it will come out within your risk analysis. When we're doing here retrofit, I guess whether you're doing retrofit or not, the other big thing is confidence in return on investment. If I'm making a change here and saying it's going to cost this much, it's going to only cost us 15% more to get net zero. The owner wants to know, what is the chance I'm really going to make this back in 5 years? You've got one of these things, you got the CDF, you can tell them, got a 95% chance that we'll make it back in 5 years, in 10 years. That's, I think, another big thing. All right, so that's talking about existing buildings and the methodology. The same thing works here. That's the idea of doing probabilistic. The last thing I want to talk here about is calibrating models for existing buildings. Before we go on, questions? Tristan had one. Anybody else? Yeah.
Of course I have. So when do you think a regular energy modeler will be able to spit out the probability for the energy model and the predicted EUI he or she is putting in a report?
For somebody who's going to, who is a user and wants to make use of OpenStudio, either whether it's direct or through some interface, you should be able to do it by this time next year. Actually, the core is already there in the next releases. There's the cloud support is there. I'm going to talk, just briefly mention, a fast energy model to make this practical is already there for doing it on the desktop. The uncertainty libraries that will give you uncertainty ranges for a lot of inputs is going to be in there by the end of this fiscal year for DOE, which is September. That's the work we're working on. So by this time next year, there will be workflow. There's a tutorial that's going to, a couple of tutorials that are coming on in upcoming conferences. SimBuild has some, because I know NREL's out giving. And we're going to be talking about one about Bayesian calibration. So this time next year. Now the question then is, how long before IESVE picks it up, and how long before Design Builder picks it up? I don't know. I've talked with IESVE, a few of the people, and they're like, yes, but they're not convinced. They're going to wait. So you have to be on the edge to get there. All right, existing buildings. So let's go ahead. We got an existing building. I know the energy use. I said that we don't, but suppose we got a measurement. I know what it is. So there's our actually energy use of the building. Got a building. I put together a model. I predict it looks like this. It's uncalibrated. We know, okay, obviously I got something wrong. If you're a good modeler, you'll go ahead and figure this out. Now the question here is, can I make this match? And that's not the question, actually. Any modeler can make the red line come down to the black dots. The question is, have you done it right? Now what we're proposing and what is going into OpenStudio is a systematic method for automatic calibration of this that takes into account the uncertainty that we started with. So one of the things is what we should really be doing on our model is putting uncertainties, given that we don't know. And if we go ahead and see the uncertainty, here's our bars. That given the uncertainty in our model, if our data is actually fitting within the uncertainty bars, which it is here, I can do automatic calibration to reduce this. If it's beyond this, I have to do, my model was so far off to begin with, I can't use automated procedures, at least not the ones that we're working on. So we have this idea, if we do calibration, this is what it's going to look like. I can easily, with my automatic system, this came out from an example, match this data up. And if I look at one of the things that's going to come out of calibration is not just I match the data, I also am going to reduce the uncertainty prediction. And that's what happens with the uncertainty of the inputs. The automated procedure takes the most important inputs that are uncertain and reduces it. So here's our uncalibrated and our calibrated all on one plot. So this is our month by month. Usually when we're done, we do this, we actually want our single number at the end. This is an idea of the probability distribution that we would get out from these models of the calibrated and uncalibrated. This black bar is the actual energy use, the EUI for the year. I added up each of those, each of these things for the month. I get 178, 177. This red, even though you look here, month by month is really small, we actually have quite a high annual EUI when you add them all up. And this mess, this is what we got out of the uncalibrated model. And actually this dip down here doesn't mean that I think I need to do a lot more runs to get a better histogram. This was only done with 600 runs, which is what we needed for the calibrated model. The idea here is, let's go ahead and talk about this procedure. Now, most of us who are energy modelers would go ahead and say, I know a little bit about building, I do have calibration, but we have a situation here. Different modelers are going to tweak the model differently. So who's right? Amir goes and says, I need to change, I've got a problem here. I'm going to change the plug load, I'm going to raise the plug load, and I'm going to drop the lighting. I'm going to change the windows and change the lighting. The interaction is such that I don't know that he's right. And if I do a different change, I don't know that I'm right. Which one's right? That's a hard question to ask. When we start putting uncertainty bounds on our inputs, we now have a constraint that's going to help us choose which inputs we can tweak. Without uncertainty, there's no basis for the confidence in the model other than the modeler's ego. And for those of you who know me, I got a big ego, but I'd rather put some uncertainty bounds on. And what you can't do is risk assessment. If I don't have uncertainty, I can't do the risk assessment other than, I really think it's about plus or minus 20%. That's my gut feeling. Don't use a gut feeling. Do some math. The Bayesian calibration procedure, what it does is you put uncertainty. I put those distributions on our inputs. And through the systematic procedure, it's going to reduce the uncertainty in those inputs, which also makes the model match the actual data. And you do this by running lots of simulations and seeing which ones get closer to the actual data. And you choose or you throw out data points that don't help you get closer. That's the idea of Bayesian, using Bayesian statistics. When we're done, two things are going to happen. Those uncertain inputs that I did calibration on, I reduce the width of the uncertain and I shift the peak. Here's an example, infiltration rate. I said could have been anywhere between 0 and 12 air changes per hour. This is actually very common if you're trying to do a really old leaky building. And when I thought that it was most likely low, but I was considering it rather wide. When I did my calibration, basically said, oh, you were pretty close to right on. However, your uncertainty is way too wide. These data out here are not consistent with the actual measured data. So the calibration didn't help my peak prediction, what I thought the value most likely was, but it did reduce the uncertainty, which means I have much higher confidence in my model. Here's an example of the thermostat set point. This is one of those great inputs. What is the thermostat number? And we went from our distribution, which was actually was a triangle. We see that as really skewed. We didn't reduce the range that much, but we shifted the peak. So this is the idea of what calibration does. How this works is we do our uncertainty quantification. We do parameter screening, which helps us figure out which ones are most important. We start out with our distributions. We go through calibration. It changes them. And then when we're done, we have model predictions using the updated distribution. So we will get out an EUI curve and a CDF just like we did for if we were doing the model to begin with. So when we're done, here we're looking at a retrofit. Here's a company, you can actually do a real risk assessment. This is a company out in California that is doing retrofit loans and insurance. What they want to do is they take their model, they generate this probability distribution curve, and they give a rating to somebody who's looking for a loan for a building retrofit based upon the confidence of the wide range of the predicted EUI and the savings that you're going to get. So here's an example of something that got a BBB rating. So they're giving this AAA through D. And they can go out to get an insurance company to either back up a loan or for the company that's trying to do the loan itself to give a rating so they can have better confidence. All right. So I told you a bunch of stuff I think is where things are going. What we're doing to enable all this is we have done three big things that I think you'll be interested in. First one is a reduced order simplified model. So that's sitting on your desktop. It takes milliseconds to run, but at least especially in early design, or if you're doing the beginning part of retrofits and you don't have a detailed energy audit, you can get accurate enough information to make design decisions or select between retrofits. And then once you've done this, you do a more detailed model for retrofit. It's several orders of magnitude faster than Energy Plus. So for it, it quite literally takes millisecond. So you can do 1,000 of them in a second, or 1,000,000 of them in a couple hours. We're working with Georgia Tech to develop uncertainty libraries, and they're going to go into the building component library. So all those uncertain distributions and the shapes and the ranges, that's going to be something that's going to be in a lookup table based upon some sound research for inputs to Energy Plus and OpenStudio. And then we're working with NREL right now to integrate the Bayesian calibration into the Studio development kit. So the ISO stuff is actually there. It's not well advertised because there's still some bugs and some translators, and we haven't had enough time to do work in developing examples. We just hired on Brendan, who's going to help us in all those things. Our Bayesian calibration package is going into the SDK, I don't know about as we speak, but over this next year. So, in summary, for new building construction, probabilistic modeling is going to help you quantify the possible and the probable values of energy use of your design, even if we're talking very early design, which helps you do things like cost-benefit analysis and lets you see if you need to improve your model when you're looking at design changes. And for existing buildings, calibration like Bayesian's calibration will help you improve the model, which lets you do real risk analysis. So I guess I'm going to summarize this at the end. Who is it you want to be as a designer and energy modeler? Do you want to be Mr. Slick, or do you want to be Ms. Thoughtful? And I'll end with that. Questions? Yes?
Would it make sense to apply these uncertainties to a conservative factor on the inputs to hit a target?
So the question being, if we just put conservative inputs, that's an easy way to go ahead and get a single number, but you still don't have an idea. That you can say, the problem with saying I'm always going to pick a number that's toward the end of the distribution is things interact nonlinearly. I can't just pick a high number on one distribution and a high number on the next. If I really understand the interactions, I could do that. And actually, what there are tools, one of the things that NREL is doing is really cool. So they're working with these distributions, and they're saying, if I know this is my target, they have systems that will kind of go backwards and show you which inputs are most important, and will tell you which range of inputs actually lead to this other output. But at the beginning phase, it could help speed things up, but unless you really have a good grasp of the interaction of physics, it's hard to do that. Because things are not monotonic. It doesn't mean if I increase this, the EUI is always going to increase. Now, usually on one input I can do that. But because of the interaction of two inputs, and I'm always looking here at variations between lighting load, what's your solar gain, and lighting load. When I go change my lights, my cooling energy drops, my heating energy goes up. I got so much interaction of daylight, the lighting energy use when I've got daylight controls, and the solar gain. That's an example of how do I pick my numbers? It is not an easy answer. If I'm talking about the COP of a big chiller, and I say they're all the same, that's easy. You're right. I could go ahead and say, I'll just be conservative. But what about the other components? If you're going to go ahead and say, I'm not sure, my argument, especially now that there's a cloud, that I can go ahead and throw it up. If I'm doing 600 or 1,000 runs, maybe that's all I have to do. They can be done in the same amount of time it takes me to do one, and it costs me 15 bucks. Right? That's what it's going to cost me to have 5 minutes of run, maybe not even quite that much, on Amazon with all the cores. Is it worth 15 bucks to get that? Now, if I'm going to do this 8,000 times to 15 bucks, maybe not. But if I'm sitting here, and so you don't want that as you're tweaking around Rhino and just mapping things out within your lab. That's what you use a fast model for on your desktop. When you're now going out and saying, we've got things a little bit more firm, and I want to use a full energy plus, spend the 15 bucks in the cloud. It's far cheaper to do that than to then spend 150 bucks for you to play for an hour to figure out which of the things to tweak and input so you can run it in 5 minutes on your desktop. Yes?
The mention of incorporating uncertainty data in the graph that you produced earlier, you are basing that on real data?
Yes.
Can you give a specific example of, what are you looking at?
Okay, so yeah, let's take a look at, there are things, something like the area of a building. What is the area of the building when you're doing, somebody goes through and doing an audit? ASHRAE has done studies of repeatability of audits, where they've gone through and paid 100 people doing an audit to go through the same building and come back and give numbers. And in this, you see that the range is plus or minus 10%, and it looks kind of like a Gaussian distribution. So that would be an example of, we're going back to literature studies. There's manufacturer data. So when it comes to things like COP, the usual way, actually, you can't just go to the manufacturer, but you look at the standard that is used for the design specification, and that standard, well, depending upon the standard, may have both a repeatability, which is one piece of equipment doing it again, and then if two different labs were reproducibility. So you look at the distribution of the reproducibility. When it comes to things that you're sitting here like the R value of an existing building, that's a little bit harder. And where you come down to is we've been relying on literature studies. That the uncertainty libraries are something that there's certainly going to be room for both people to contribute and room for improvement. And I think this is where, so a lot of people say, well, if we do this, all the secret sauce that ESCOs have will go away because they've got their own ways of doing energy computation. No. What's going to happen is ESCOs will have, from their own experience and database, their own values that they want to use for uncertainty. I don't think it's going to make things any worse. What it's going to mean is those ESCOs can reduce their overcharging that they do now, instead of, which works for the mush market, municipalities, universities, schools, and hospitals, because they can afford to pay. But they're not, the ESCOs are not going into the commercial market, especially small buildings, because they pad their energy savings numbers to cover risk. And they just can't afford to go into buildings until they can reduce their risk. And if they can basically say, oh, instead of me doing so much padding, I can do uncertainty, they will be able to go into that market. And I see ESCOs and on-bill financing as a combination, or PACE financing, where it's done through state systems. Lots of new ways of financing when you can do risk analysis. Does that help answer your question? Even though it morphed?
We were talking. I mean, we've been talking about how you integrate these types of tools in early conceptual design, and I think that it'd be good to hear you talk about how do you think that as there's kind of an advent of tools that are coming out. I want to identify Autodesk as saying having these tools that say, well, if it's an office building and it's this much area, this is what your EUI is. That oversimplifies something that I think that during the conceptual design you're not necessarily looking for a number, but you're looking for, okay, you're trying to use that design space to identify sensitive issues. Here, if I rotate the building this way, it has a bigger impact on the overall energy usage than another variable. Do you think that there's sensitivity issues that are able to be, do you think there's a methodology by which you could say there's uncertainty in these sensitive issues, so you could identify, okay, these are the 20 or 30 variables that we should be looking at, and these are the ones that you as the designer could be influencing, yes, or you as the HVAC engineer?
Actually, that is a very good question, and I think one of the tools, whether it's our tool or somebody else's that's going to be useful, are the reduced order models that capture enough of the physics to give you the envelope orientation sort of situations, which is what you as an early designer are often playing with, and the solar game. When you have a model that can quite literally run in a millisecond, so Rhino can't run anywhere near as close to dump stuff out. You can have something where there's uncertainty in those parameters based upon what's coming out of your parametric Rhino. And it's producing, as you speak, those distributions, because it takes a second to generate a basic distribution. So as you go ahead, drag your Rhino or program it up to give you 50 different orientations of the building, you can come out and see that distribution change its shape and size as it goes in space. That is something, and you can see, and the reason you want to do this instead of just a single number is you can see, all of a sudden when I change the window to wall ratio, because of the interaction, I go from low uncertainty to big uncertainty. That doesn't mean not do it, but that tells you, ooh, this is risky. And I do think that these fast energy tools, DOE is unfortunately not able to go ahead and say, oh, they cannot pay for something that plugs into Rhino. They can't have something that plugs into Autodesk. Autodesk is doing their own work. They've converted Energy Plus, so who knows where they're going to go. But Bentley and Diva, Rhino and the whole crowd that's doing Rhino and Diva and Grasshopper, if we can get some other people to support that research, DOE actually can, through something called SBIR, Small Business Innovator Research. So this is something that I think I tried to get some stuff going this year. It did not work out. Next year, the people who are developing a lot of those tools, they can maybe get a funding stream to help develop them, because the stuff that you guys presented a few times back, that is incredible. That is an incredible tool that can be linked up. So as you're running, you're playing with your haptic interface to do that design, whether it's that way or something else. Two things. Even if you skip the uncertainty and just get the fast update, I think you can, by eye, see where things are more sensitive or not. And the methodology that we use in the Bayesian calibration for sensitivity to select the variables could be used just as easily as you are talking about to say, these are the 10 most important things in my envelope design that I need to worry about as far as my impact. And these have a higher impact, given a base model, than the HVAC components. Or here, the HVAC component is more important. So as much as we're playing around, don't forget the HVAC component. So I think in terms of that ranking, the tools almost exist now. When you couple to uncertainty, it can help you make the decision more clear.
I have a comment to Anthony. So, I think the biggest contribution of knowing the uncertainty and the margin of error would be that when you have a very overly simplified tool and you see a UI reduction of 2 kBTUs, it doesn't mean that it's better, right? It's because if it falls under the margin of error, it's actually insignificant for an energy modeler to say it's going to be better decision, right? So basically, maybe like a 10% of our recommendations will just go to trash because we can't actually say with confidence that it is better because it reduced by 2 kBTU. But if I have, let's say, the margin of error of 10 kBTU, then it's right in there. It's not significant.
So one of the things that are going on is, as I mentioned, energy modelers are liars. I want the whole design team to be more cognizant. There may be reasons you want to go ahead and make that change. It's an aesthetic reason that you want to make this change, just because it's fitting in with a lot of reasons. And then people will ask energy modelers, is there a difference? There's 2 kilobtu per square meter. And it's not within the margin of the uncertainty. I don't want to see people making that as a reason for doing it. And the reason being is when it gets done and built, because it's outside, you didn't see what you expected. That ends up making people less confident in the results. And if there's a good reason for, whether it's aesthetics or some other design philosophy, in terms of, it just makes the flow of the building better. It really makes the functionality better. If there are other reasons, I don't want to see people going and claiming energy use as one of the reasons when uncertainty doesn't dictate it's a good one. Because that leads to, if the energy prediction was wrong, that's with an uncertainty, or it didn't help, that leads to people having lesser confidence. If there is a functional reason for you to make a change, argue the functional reason.
Well, and that was, I guess, the question was just it was that I know that that's a complex negotiation. I just wonder if we as designers, of course, are like, this design is having a huge impact on the energy usage, when in fact, I mean, it's overcomplicating something that's like, you could put daylighting controls in, that's 10 times more energy savings from that. Okay. And I think that's how do you understand that complexity, that it's not an oversimplified, hey, this is, by changing this one variable, you're going to save a certain amount of energy. You all of a sudden understand that, hey, if I do this, there's actually ramifications that change what my, if I change the orientation of the building, that has a big impact on, or the other things that are like the top 10 next things that you should do, all of a sudden reshuffle and say, hey, this is actually what you should be looking at.
So one of the things that NREL has been doing, if anybody here has been familiar at all with OpenStudio, there's the main package, but there's a new thing that they call the parametric analysis tool, PAT. And within PAT is something called measures. Now, until the last release, there was very few measures. Measures are basically things that you will do to a building. And you can think of it as what Rhino does. And terms of, oh, you go ahead and morph the window-to-wall ratio, you head and do this, you change orientation. So measures are ways of changing the basic building design. But measures in the case of OpenStudio means I can change HVAC systems, swap them in and out. I can go ahead and change the zoning. Now, they are developing for other clients. I can't name who some of them are. You have to get me a lot more beer before I do. They are developing sets of measures to basically think about the stuff that you're talking about. So as you're doing this in Rhino, they're putting together the base package that you could evaluate those measures. They also have just developed and released almost all the measures that are part of the Advanced Energy Design Guide. So for those of you who are familiar with that set of design guides that was put forth by ASHRAE, that says, oh, here's a hospital. There's a 50%. These are the things in hospitals. And if we go ahead and do lights, this is your expected energy savings. And if you want to get something that's 50% less energy cost, here are your kind of recommendation of different things to do your building. And what they do with the measures is you give them a base building design, and then they go ahead, through their measures, transforms it to meet the recommendations of the 50% design guide. So if I've got a tall office building, I take my office building model, I push the button, and it's like the 50% guideline window-to-wall ratio. It goes, I wish I had the video. It goes and takes your windows, puts them on the right facing, the window to the wall. So the south has got much larger window-to-wall ratio to capture daylight. The east, west, and north walls have much lower window-to-wall ratio. So it's not just it goes to 40%. It goes and follows the guidelines to optimize the window-to-wall ratio based upon your climate zone, your how far, yeah, I guess that's part of your climate zone. Your climate zone, the weather conditions, and it modifies your building much the same way that you would try to do it in Rhino. It is really amazing the tools that they are putting together. Now, unfortunately, it is still not a designer-friendly package. It is absolutely not a designer-friendly package. So there needs to be developed to get to that next level. But the tools that they're putting forward, both with the measures that they have and their version of optimization and their parametric tool for once I've got a whole slew of options working backwards to help choose, that if I wanted to do a more parametric, not just the uncertainty, it's like, let me do a sweep over this range of possibilities of window-to-wall ratios, orientations, and they set up to set it out to a cloud, come back in an hour or 2 hours with 1 million runs. And then you say, which of the ones here have the EUI in the range I'm looking for? It then works backwards to show you all the possible design procedures. That is a really cool tool. That if there can then be an interface to the way that you design, the way that you're thinking, that's where things need to go. Yes?
Regarding that uncertainty quantification for the input, you said it's like so complicated process. I was wondering, for example, it depends on the stage of the design. For example, for U value, if you are at the later stage of design, for example, you have decided that you want to have 0.2 U value for one.
Yeah.
The uncertainty that relates to that one would be different from the very beginning of the design.
Very much so, yes.
That we haven't decided about anything.
Yeah.
So the thing is that because I'm working on exactly uncertainty quantification at the earliest stage of the design, so my main question is, based on your experience, do you think that because at the earliest stage of design we have a lot of high level of uncertainty, and the spread of the probability would be the probability would be so spread? Can we really make decision at that stage with confidence that we get a specific result?
I'm going to say, of course, I'm going to have to equivocate. Depends. When we're sitting here in the very early design phase, instead of a narrow distribution with a peak, we often would end up using a uniform uncertainty, somewhere between here and here, because I can have 5 different wall types. And the answer in terms of how that's going to interact will depend upon the sensitivity to that variable. What I personally rather go ahead and say, all right, does it help me in my decision? Maybe not. But at least I then realize that my Y variation walls and the uncertainty completely swamps any of the window to the wall ratio changes I'm doing. That's an important piece of information to know. Does it help you with your design? No. It doesn't help me then choose my window to wall ratio based upon the energy use. That's an important point. I guess the point being, oh, I changed my window horizon and things are going to go up and down. And the answer being, it depends upon how much I'm going to, what my wall U is. It tells you I need to be careful about the interaction of the two. And I should not make a design decision on window to wall ratio completely, or at least I better look back at it. So I understand your question of when I've got an uncertainty that's so wide it swamps everything else, how can I make a design decision? And I think that in itself is an important piece of information. But I don't know how, it doesn't necessarily, the information doesn't help you in the design, but it does help you understand the problem better. And I think that's still an important thing. So I would not suggest, and I think that's an important point, and for those of you on the videotape, this is not to say that uncertainty helps you always make a design decision. In fact, uncertainty can often make design decisions even more difficult to make. But I would argue that means you weren't thinking hard enough about it to begin with, because it really was a hard decision to make, and you were making it easier than you thought it was.
Yeah. And just
uncertainty's good.
Yeah, regarding those two questions that asked about area design decision, just because I'm working in that group of Georgia Tech with Edinburgh, my research is about exactly that earlier stage of design, and until now we have developed a method. This one is like so new, but exactly in line with what you said. That at the earlier stage of design, when we want to compare two design options, then we quantify it in terms of confidence. It's not only about the difference between the mean value, but we have like proposed some like confidence level that one is enough better than the other based on the probability distribution. And then in most of the cases, we won't have enough confidence to decide between two options, but in some of the cases, yes, we could. And specifically in a very like harsh climate zone, we could better make decision about the design options rather than the other like sort of climate zone.
Okay.
And yeah, so.
But there's really a whole set of other constraints here. This looks strictly at, you're strictly looking at energy modeling, you're evaluating systems and costs, but on any given building, your choices are never infinite.
Right.
If you're building a warehouse, there's a narrow range of construction types that you're going to build within. If you're building a residence, if you're building a high-rise tower, you're always constrained by a number of those things. So your real differences are, I'm building an all-glass building. Is it better for me to do 2 panes of glass with low E, argon, and shades? Is it better for me to do 3 panes of glass? And how do I evaluate that energy cost versus the construction cost? Because that's if there's any constraint in all of this, construction cost is always the driver. At the end of the day, your client has a fixed amount of money, and you've got to optimize your building.
Again, yeah, so coming back, actually, that's a good point. The tools that I mentioned, NREL is putting together with their parametric tool. The other thing that they're hoping to put together is cost database. So right now, in part of the retrofit, they've got Energy Plus has economics in that people don't use. That information is being coupled in along with it, so that as I show those little graphs of the uncertainty, you can do uncertainty in both. Now, I don't know a good uncertainty. Actually, I take that back. I do know a fairly decent place to get uncertainty information about costs, and it's a matter of getting subscription to means, and not the book, but the actual database that they use, because it's called RS means because they do averages. So it's a matter of they go ahead, they've got their statistics and where they got all the data for it. That's what you need to get access to, because the higher end scheduling and planning tools have subscriptions, not just the means data that's in the book. They actually get out to do the longer term probability. That'll be an interesting thing to see if I can find some money to be able to connect up to the means database and throw that in there. Somehow I don't think DOE will pay me to do that one either. All right, well, thank you. So there we go. Oh, anybody know where this picture was taken? It's a picture off the beam. It is a little fuzzy. It was taken on my cell phone after